Hello, welcome to the afternoon session. So I'm going to be talking to you about sidechains protocol for Ethereum Classic that we have been working on at the IOHK, also at the University of Athens, where I'm my PhD candidate. So this is a nice slide that I like starting with. So here you see two blockchains. One is at the top, the other one's at the bottom, and something's happening between them. So this is what we want to do when we talk about sidechains or cross-chain transfers. You have something going on at the top, like at the black block. So here you see a blockchain that is evolving with time, and something's occurring. There is some sort of event, a deposit, maybe a smart contract event, and we would like this kind of reaction to occur at the bottom. So this kind of sums up the whole idea. So what are we trying to do here? So here we have two blockchains, and in this talk I will use the example of Ethereum and Ethereum Classic, but really you can have any two blockchains interface with each other as long as they have some sort of smart contract support. So Ethereum and Ethereum Classic are the perfect example of this. So what we want to do is when something occurs, when some event happens on one of the blockchains, like the frog here, on the original chain, after a while this event is somehow propagated to the other chain, and the other chain learns about this event. And of course, there have been some attempts to do that in the space, and one idea is to have some trusted parties attest to the fact that this event took place, like a committee or a federation or just one party or majority of signatures and so on. But the way we want to do that is in a decentralized manner, in a trustless manner in which you don't really need to trust someone to be telling the truth. So as long as these two chains are on their own, they're secure and honest, and they operate safely, these events should be able to occur without the need of a trusted party. So this is the goal that we're trying to achieve here. So just some terminology before I go into the details of how we're making this happen is when we're making these kind of event transfers, we have a source blockchain and a destination blockchain. Here in this case, it will be Ethereum and Ethereum Classic. And this would allow interfacing between the two. And I will describe this as the top as the source and the bottom as the destination. However, this is just one event transfer, and if you have the ability to do that between two chains, both downwards and upwards, then when you're doing the upwards direction, the source and the destination chains are reversed essentially, and the bottom chain becomes the source chain and the top becomes the destination chain. So ideally you would want to have bidirectional communication between your blockchains. So in this case, we're talking about proof-of-work blockchains. We also have a way to allow proof-of-stake blockchain communication. We're working on this with Cardano specifically, but in general, it should be possible to work with any stake and any work blockchain as long as there is some smart contract support. So in this presentation, I will talk about just work communication. But one thing we also have the ability to do is to interface between work and stake. So there can be also a hybrid protocol. Okay. So what kind of events can we transfer? What kind of events can we make known from one blockchain to another? So really, if you are a developer that writes smart contracts in Solidity or if you're familiar with what you can do in Ethereum or Ethereum Classic in terms of firing events or calling smart contract methods, anything that you would be able to do within a blockchain, so calling into a smart contract method or firing an event, you can do that in cross-chain transfers. So you can have an event that, a particular block was generated or an account balance was changed in this way or a particular smart contract method was called. So that's the goal here. And now I want to go into some details of how we do that. So now let me tell you what is the status of being able to do that and what kind of upgrades we need to the underlying chains to be able to do that. So for Ethereum and Ethereum Classic specifically, We are working on implementing it first on Ethereum and Ethereum Classic because these are two Turing-complete chains, and this is convenient for us. So one of the things that we need is what we call a velvet fork, which will need to happen on the source chain. And this is something that can be user-initiated, and we're working on doing that. And then the other thing that we need is to have it be gas efficient on the destination chain, in which case we need some sort of opcode. But this is not necessary for it to exist in general, just for it to be gas efficient. So this is an Ethereum Classic improvement proposal that we have put in earlier this year to make these smart contracts more efficient so that these events can be reacted to without spending too much gas. So right now, the implementation that we have is somewhat gas expensive, but it does work. OK, so now let's go into the details of how this is done. All right, so really the challenge in making this happen is that we have these underlying chains. We have the Ethereum chain and the Ethereum Classic chain. And these two chains have miners that don't really want or care about monitoring the other chains, right? So if we wanted to make a hard fork, it would have been easy. We could have said to the, let's say, to the Ethereum Classic miners, oh, you guys, you need to look at the Ethereum blockchain as well and monitor this network as well. But this is not what we want to do because this is impossible for it to happen. So we want this to be isolated. We want the miners at the top and the miners at the bottom to each maintain their own network and their own blockchain without being aware of the other chain at all. So that's really what is making this challenging. So the way we do that is we create these little things that we call proofs of work, or non-interactive proofs of work, which is a primitive that we have invented with my advisor, Aggelos Kayas, back in Athens, and in a collaboration with Andrew Miller as well. And what these do is they take a blockchain, so they can be generated by a full node or an SPV node, and they take a blockchain and they compress it into a very short string that is just a piece of text. Then you can take that piece of text and post it on a different blockchain, proving that something happened. So this is the underlying cryptographic primitive that you can use to make these things happen. So I will not go into details about how these are generated, but I will give a link to my paper at the end so you can take a read. So this is the basic building block there. So here is the recipe for doing this. Whenever something happens on the source blockchain at the top, then a user that has seen this event can generate this proof of work that this event happened. Once this proof of proof is generated, this can be included in a smart contract call to the destination. And this call is not via the network. It's just something that you can do as a user, as a regular transaction in which you just submit a string that can be independently verified on the destination chain. So the smart contract running in Ethereum Classic here can just check that this proof is legit, it's valid, and then react to this event accordingly. So with this, you can do some very interesting things. And my favorite example is a two-way peg, in which we can create in Ethereum Classic an ERC20 token, which is pegged to one Ethereum. So then you can use all the Ethereum Classic features that you may want, but for units of Ethereum and not Ethereum Classic. So here's the idea. At the beginning, you have a smart contract living on Ethereum and a smart contract living on Ethereum Classic, and these are kind of sibling contracts. What you do is you deposit some money in the Ethereum smart contract, and once this money is locked up there, you use this, you create a proof of proof for this event, and you include that proof of proof in a call that you make to the smart contract that exists in the Ethereum Classic chain. And then this smart contract generates for you, it mints some new units of an ERC20 token, which are exactly equal to the amount of units that you locked up in your Ethereum chain. So this is the generation of new tokens. And then these are classic ERC20 tokens, so you can move them around in the Ethereum Classic chain as if they were any kind of token. You can transfer them, you can delegate them, whatever you like. You can split them, you can merge them. And then eventually, as they change hands, somebody wants to bring them back into the Ethereum chain. So in that case, what they can do is they can deposit again to some sort of withdrawal function in the smart contract, which destroys the ERC20 tokens here, and then provide a proof that this destruction took place, and then restore these tokens in the original Ethereum chain. So this allows you to have essentially bidirectional communication, and because you can always bring money back and forth between Ethereum actual native units and the ERC20 token on the Ethereum Classic chain, these two tokens are essentially pegged to one another without the need of any central party ensuring the pegging. It's just a decentralized kind of peg. Okay, so that describes what happens. So here I have a smart contract showing how we can do that. And I know this is unreadable, but we will put up the slides on the website. So you can take a read on your own. So it's a couple slides here. And then I'll also give you the references for our papers. So mainly this is a paper with Aggelos that is still unpublished, but we're working on publishing it very soon. And this is how to create proof of work sidechains. So the blockchains that communicate that are based on proof of work. We also have 2 more papers that are ongoing. One is for proof of stake blockchains in collaboration with Aggelos and Peter Gaggi, which is also unpublished, but we are also publishing this very soon. And also we have a paper that is already on ePrint since last year actually, but we have been updating it very actively, which is called the non-interactive proofs of proof of work. And this describes the underlying cryptographic primitive, which you can read to see how the construction exactly works. There's also this website here, nepopaus.com for non-interactive proofs of proof of work.com, right? And here we put up all the papers that are related to this kind of construction. So you can check back here, and it has some nice descriptions as well for how this works. So that's it. I want to leave some time for questions if any of you have questions. So, and thank you very much.
All right, do we have any questions? Come on, somebody's got to have a question. Oh.
Hi, great talk, thanks. This may be a stupid question, but I was wondering if the non-interactive proofs you've been talking about here are at all related to the Genesis proofs in Ouroboros Genesis.
I don't know how to answer that, but we can take it offline. I can check with Aggelos, who has invented Ouroboros Genesis, to see what exactly is the relation. But I don't know the answer to that. Okay. I don't think that's a stupid question. I want to research that. Yes, Charles. Microphone?
Thank you so much. Hey, sorry for missing part of your presentation, but I know a little bit of the research. I have a question about light clients. Have you guys run any numbers of what type of efficiency gains Nepopaus can provide to a proof of work light client?
Yeah. So one of the applications of Nepopaus, because they can provide these short proofs that something happened on the blockchain, is that they can basically compress the blockchain not only for cross-chain transfers, but also for light clients. So in theory, this allows what we call exponential gains. So instead of maintaining the whole blockchain, what you can do is you can maintain a small logarithmic part of it. And then this allows you to have a much lighter client, especially as the blockchain grows. So yeah, we have run some numbers on, for example, the Bitcoin blockchain. And in that case, we can reduce the blockchain from what it is to down to maybe a few hundred kilobytes, like 100 kilobytes. So that would be a concrete number there. Yeah, that's useful for replacing, let's say, SPV clients to make them even lighter. And I think the related work that we're doing in proof of stake is actually the first to be able to do that in the stake case. So that's also very interesting.
Awesome. So I had a question too. You mentioned Velvet forks.
Yeah.
Do you want to explain a little about how they work and how they might be different or somewhere in between soft forks and hard forks?
Okay, yeah. So Velvet forks are a kind of fork that we invented for non-interactive proofs of work to make them less intrusive. So in fact, a Velvet fork sits not between a hard fork and a soft fork, but it's actually softer than a soft fork. And actually there's, if you go to this website here, nepopaus.com, There's a follow-up paper by Zamyatin and his collaborators that was published in last year's Financial Crypto, which expands on these ideas and talks exactly about what a velvet fork is. The idea is that when you have a hard fork, you break backwards compatibility. When you make a soft fork, you have a backwards compatibility, but you break forwards compatibility. But with a velvet fork, you maintain both backwards compatibility and forwards compatibility, which means that the upgraded miners will need to inject some new information into the blockchain, but the old miners can still mine valid blocks that will be accepted by the new miners, and vice versa. So every old miner will accept new miner blocks, and every new miner will accept old miner blocks. So some blocks will have additional information, and some blocks will not have additional information. And if we have some percentage of miners upgrading, even like 10%, we can still have this kind of construction. So we don't need majority miner approval to run this protocol. And actually, we have also something called a user-initiated velvet fork, in which, in fact, we don't need any miner approval at all, and the user can just inject this kind of data that we need in transactions that occur in blocks. And this is different from application data. It's consensus-related data that we inject into the blockchain. So yeah.
Does the user-activated one require like a certain amount of nodes to actually make the velvet fork work?
Yeah, but they don't have to be mining nodes. They just need to run some full nodes. And the users that do this kind of injection, they don't have to be the ones that use the protocol either. So.
Okay, great.
Yeah.
Do we have any other questions? Oh, back there.
Hi. Great talk. I really appreciate the work that you're doing.
Thank you.
Do these ideas deal with the Sybil attack in any ways differently than a normal SPV-like client would?
So the way that we deal is comparable to an SPV client. Now, so our security proofs that we do and our security theorems always achieve almost the same security that you would have in an SPV case. So you don't have a stronger security than that you would have in kind of a full node scenario.
Got it.
So these are not, so if you've seen other protocols like Coda, for example, where they do a full zero knowledge history attestation of what happened, this is different. And in their case, they provide some full node security. This is SPV node security.
Also, how is it more compact than SPV proofs? I just don't quite understand that.
So in SPV proof, what you do is you provide block headers, but for the whole blockchain. Mm-hmm. In our case, you just provide some indicative blocks that you choose, a small sample of blocks, which is logarithmic to the size of the actual blockchain. So if the blockchain itself is like 500,000 elements, like in Bitcoin, you would have to provide something like 20 sample blocks that illustrate, not 20, but maybe a few hundred, just to illustrate what happened on the blockchain, but without replaying the whole blockchain.
Interesting that you have the same level of security.
So this is exactly the construction that we have in the Nepal paper. And this is exactly the reason why we need the velvet fork, which basically allows the blockchain to be deeply connected, and you don't just follow previous block pointers.
Got it. Thank you.
Yeah, you're welcome.
All right, great. Any more questions? Okay. Thank you very much, Dionysis.
Thank you.